Hello everybody. Today we will be talking about the law of mass action. While we qualitatively described the law of mass action in the past video, we will now be talking about the law of mass action in quantitative terms. This means that we will finally be working with math for the first time in this course. First, let's review the law of mass action. The law of mass action states that the rate of the reaction is proportional to the initial reactant concentration. Again, there are going to be three factors that determine chemical equilibrium, and that is initial substrate and product concentration, temperature, and pressure. The law of mass action justifies that the initial product and substrate concentration affects chemical equilibrium. There are first two important assumptions that we must have in order for the law of mass action to be accurate. First, we must have a well-stirred or uniform solution, and the second is we must have low molecular concentrations of the reactants. We must have the first condition of uniform solutions because large variations between the spatial regions between reactants may lead to gradients and waves. The other condition, low molecular concentrations, also ensures that there will be a point of equilibrium between the reactants and products, because if there is one much more larger concentration, this can lead to supersaturation and thus chemical equilibrium never being reached. Now we will be showing the general form for a mass action reaction equation. In this equation, we can see that we have the lowercase s1 and the lowercase p1, as well as the uppercase s1 and the uppercase p1. The uppercase s1 and p1 represent the variables that define the substrate and product. The lowercase s and p values represent the coefficients of each of these s1 and p1 uppercase products and substrates. So for our first example, we will be looking at a simple mass action chemical reaction. In this mass action reaction, we can define the four elements of this reaction being the uppercase A as the reactant, the uppercase B as the reactant, Kf as the forward reaction rate, and Kb as the backward reaction rate, and finally, C being the product. We will first be modeling without numerical values and see how we can use these differential equations. So now we are going to be writing the rates of change for A, B, and C based on the Kf value. So you may be wondering how we derive these rates of product formation. We obtain this by first determining what rate we want. First, let's go over some notations. The brackets around A, B, and C represent how these are the concentrations of the parts of the chemical reaction. The Kf is the forward reaction rate, while the Kb is the reverse reaction rate. So now let's begin to step by step find the rates of the change in concentrations over time for A, B, and C. Let's start with the change in A's concentration over time. We can split this equation into two parts. A's decrease in concentration over time and A's increase in concentration over time. First, we will focus on A's decrease in concentration over time. In our chemical reaction, the concentration of A will decrease during the forward reaction when A reacts with B and turns into C. So our first part of our differential equation is negative forward reaction rate times the concentration of A and times the concentration of B. This is showing how much the concentration of A is decreasing as it is reacting with B and producing C. Now we will be focusing on A's increasing concentration over time. In our chemical equation, the concentration of A will increase during the reverse reaction where C can revert back to the initial reactants A and B. So the second part of our differential equation is positive reverse reaction times the concentration of C. Now we have the final equation for the concentration of A's change over time. It is equal to negative forward reaction times the concentration of A times the concentration of B plus the reverse reaction times the concentration of C. This is actually going to be the same equation for the change in concentration of B over time. Because if you think about it, while it may not intuitively initially make sense, this is because to have a chemical reaction, both A and B will change at the same rate, even with different initial concentrations. This is also because we do not have the stoichiometric coefficients that are different from A and B initially. Finally, what is the rate of change for the concentration of C? It is actually just going to be the negative of the change of concentration of A over time and the change of concentration of B over time. Now we will be showing the equation of a simple enzyme catalyzed reaction and how we can use the differential equations that we discussed to describe the relationships in enzymatic reactions. It is important to note that this will be considered a simple enzymatic reaction because we will be only having one rate of reaction unit, K, instead of both having the forward and reverse reaction constant. Based on this simple enzyme reaction, one of the first things that we must initialize is that there will not be a change in enzyme concentration over time. This is because, as we learned in the Introduction to Enzyme video, an enzyme is not altered or consumed during a chemical reaction. Thus, the enzyme concentration will not change over time. However, it is important to note that the concentration of A, the substrate in this reaction, and the concentration of B, the product of this reaction, will change over time. Again, we should apply the same process that we did to the previous equation to find the rate of the change in concentration for A and B. So first we'll be finding A, and we'll be doing this by doing A's decrease in concentration and A's increase in concentration. One thing to note though is that unlike the previous equation, there is only a forward reaction rate in this chemical equation. This means there is only one direction that this chemical equation can go. This type of reaction is called an irreversible conversion reaction with enzyme catalysis because there won't be any reverse reaction from the product B to A. We can see that there is no way for the concentration of A to increase over time because there is no reverse reaction. Thus, the only way that the concentration of A will be able to change is to decrease. We can thus determine that the rate of change in concentration for A will be negative K times the concentration of A times the concentration of E. Again, this is taking the initial concentrations of the two reactants, the concentration of A and concentration of E, and then multiplying it by the K reaction rate. Now, similar to the change in the concentration of B, it will be the negative of the change of the concentration for A. This is because the rate that B increases will be directly proportional to the rate that the concentration of A decreases. Thus, this will parallel our other example, and the change of concentration of B over time will be K times the concentration of A times the concentration of E. Now that we have learned the law of mass action and have seen how it could be applied to some simple chemical reactions, we can dive into the concepts of Michaelis-Menten kinetics with this background. Before that, we will be having a couple of questions and more examples in the applications of law of mass action problem set to help solidify your knowledge. Thank you very much for watching this video, and we hope this was helpful.